And we're off. First of all, anybody doing something fun over the weekend? Who's doing something fun? Fun?
We're marking the volleyball games this weekend.
Oh, is that right?
Yeah.
Yeah. And what does that require?
I basically just sit there and watch.
Oh.
Or tape. I tape people's ankles or something.
Oh, I got you. Okay. All right. Well, good luck. I hope if you're taping people's ankles, I hope you're very bored.
Probably.
In other words, I hope everyone stays healthy in the game. We're talking about all the fun we're going to have this weekend. Heidi, you got any fun? You going to have fun this weekend? Game in Oklahoma. So that's a van ride. All right. We're in Oklahoma. Do you know? Oh. Well, shout really loud, "Hi, Leah!" and say hello to my daughter. She's in Oklahoma, so I'll just tell her somebody's coming to say hi. My daughter, son-in-law, and grandbaby. Oh, the cutest little grandbaby in the whole wide world. She's right there, down there. She's in Oklahoma. Both my girls. What else? I'm doing some honeydew things this weekend around the house. Mainly church things on Sunday. What are you doing this weekend, Miss Emily? Oh, you're play.
Yeah, I know I'm working tomorrow too for a little bit. Good.
All right. Mars?
Going to Columbia.
Oh, that's right. What's his name? Jesus told me that. So that's 6 hours-ish. Well, no. Check that. If somebody from YC is driving, make it 4.5. Just kidding. Not. Have fun. Cassie says she's not doing anything, which I don't believe. Hey, how you doing?
What up? Can I sit in on the spot?
Sure, you absolutely can. This is statistics. Statistics.
I can't find my professor, so.
Oh, okay.
Yeah, I was
lost
in
it.
the office and he wasn't there. I was like, well,
Yeah, I don't know.
you know where
didn't say
Dr.
anything.
Kretz is today?
Dr. Kretz? I have not seen him all day.
He's sick? Yeah, so you're probably not having class. Or maybe it's online.
Oh.
I must have missed an email or something.
Oh.
But there was 2 other students that were like,
Uh-oh. Well, I'm sorry. Dr. Kretz is sick today, so I'm sorry to hear that. I have not seen him today, so that is very. My office is right next to it. Well, we left off last time. We were talking about Z-scores.
I have a question.
Oh, yes, ma'am.
Are we having a quiz on Monday?
Oh, yes. And it will be chapter 6. You know what? Hold on here. We have Poisson distribution. I'll tell you what we'll do. We'll make the quiz Poisson distribution. I want to make sure you guys look at that. Poisson. And I tell you what. Let's just make it just Poisson. Just the Poisson distribution. So none of chapter 6. Now, the crunch line on that, the bad side is that for the next Monday, we're not going to have all of this, but it'll be over maybe a little more of chapter 6. Because we're just getting into chapter 6 now and how far we'll be in. So we'll just make it just the Poisson distribution. One distribution, but it's kind of the spooky one, right? Number of incidents in an interval, that kind of thing, right? Yeah, good question, Ms. Emily. So Poisson distribution quiz Monday. Okay. So anyway, okay, so we left off last time. We're talking about Z-scores. And who can give me a cheap street definition of a Z-score? Give me even a bad one. I think it's time for the Jeopardy jingle. Oh, she said. Oh, boy. Okay, here we go. I'm telling you, it's push has come to shove. This is really, really, here we go. Ready? Oh, no, we got
Irish spring body wash or on your shower.
You have that pulled up. Have it saved on its phone.
I have it saved. 30 seconds to come up with a cheap definition of a z-score. Boom, ba-dum, boom, 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 boom. Boom, 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 boom. Okay. Chief definition of a z-score is?
It's the standard deviations above or below the raw number.
The mean. That's a very, very close, Brianna. Thank you. It's the number of standard deviations a data point is away from its mean. So the units behind a z-score are standard deviations. The units are not whatever units the data are in. So if the data are years, years cancel out. And I'm going to show you in a calculation here in a minute. We did last time, actually. This one here. In this particular example, you had a mean of 4.6 years, standard deviation of 0.6 years. This is from last time. To calculate a standard deviation, you take X is your data point. You subtract the mean, divide by sigma. So in this case, it's years. So you're going to have years on top, years on the bottom. The years units cancel. And those of you in natural sciences are used to units canceling and not and all that, right? So here, you're asked, what's the z-score of a full-time student who graduated in 5.1 years? You take 5.1, that's your X. Subtract the mean, 4.6, divided by standard deviation, 0.6. I'm going fast because we did this last time. That came out to 0.83. Now, what does that mean? It means that
That data point is 0.83 standard deviation from the mean, right?
above the mean, exactly. And it also means that this data point is 0.86 standard deviations above the mean. The original one, okay, it's still 0.86 standard deviation. So if you did, or 0.83, excuse me. So if you did 0.83 of 0.6, that's how far this is above the mean, right? So let me put it to you a different way. I'm going to say there's 3 or 4 different ways or 2 or 3 different ways that are all the same. Okay, that's one way. Another way is 5.1 lies in its bell-shaped normal distribution in the same position as 0.83 lies in a standard normal distribution. You remember, if the mean is 0, standard deviation is 1, that is a standard normal distribution. That is the distribution for which we have tables, right? Right here, the positive and negative z-scores. See now you see, that's why this doesn't say normal distribution at the top, although it probably is on there somewhere. Here, actually, it says standard normal right there, right? Now, this formula card is up on Canvas if it didn't come with your book, right? I suggest printing it out, and I even have mine outlined in highlighter, because when I'm doing a bunch of stats problems, where's that paper, you know? And so I have it highlighted. If I see a highlighted page, I know that's my formula card, not just another sheet of paper. All right, so that's another way of saying it, is that 5.1 lies in its original distribution, and this is the distribution of graduation times of podunk college students, right? But we don't have a chart for this. We don't have a table for this, but we do have a table for that. And that is why we transfer things to standard normal. Of course, we're going to learn to do all this on the calculator. Some today, okay? Next one, find the z-score of a full-time student who graduated in 3.9 years. So here, 4.6 years, well, that's not too bad. 5.1 years, that's not too bad. That's not so bad. I need to get somebody who graduated like 6.5 years, and somebody's name on campus will come to mind. There used to be a bunch of names of people who were here forever. 3.9 years. right? This is more of a Shannon Linen. When she was here as a student, she graduated in 3. Blew through. Find the z-score of a full-time student who graduated in 3.9 years. What do? That's x, subtract the mean, divide by standard deviation. So 3.9 is in its distribution, and the fact that it's less than the mean tells you should expect a negative z-score. Even though this is not negative, it's going to be below the mean. It's going to be anything below the mean is negative standard deviations from the mean. So you subtract the mean, divide by standard deviation, minus 1.17, that's here. So 3.9 lies in its distribution in exactly the same place that minus 1.17 lies in its. And another way of saying that is 3.19 is 1.17 standard deviations below the mean. We're going to need that. Next one, find the z-score of a full-time student who graduated in 4.6 years. How about if you graduate right in the average amount of time? Well, you subtract 4.6 from 4.6, you get 0 up top. Divide by anything positive is 0. So this lied. This is right at the mean in its distribution. You would expect it to be 0 standard deviation from its mean in the standard normal distribution. So z-score of 0 means it's right at the mean. All right? Computing normal probabilities. Now, I mentioned this last time. Right up here, still from the quiz, geometric PDF, right up there. That gives you the probability of observing. Oh, what is x in a geometric distribution? Yeah, that's half credit. It's the value. X is the value you're looking at, but instead, in a geometric distribution, that means the
trial that you're looking at.
Yeah. But we know more about that trial. There's one other characteristic of that trial.
The success occurs?
The first success occurs. The first success occurs. So if I have a die, right, and my outcome is roll a 6, right? And so that's going to be a success. All the rest of them are failure. 1/6 chance of rolling a 6, 5/6 chances of not. X would be the trial on which the first 6 is rolled. How many rolls does it take to roll the first 6? And the probability, that's what X is there, right? Now that, you stick in an X, and it gives you the exact probability of that happening on that, for that X, right? It's different in the normal distribution. It's different for all. It's different for all continuous distributions, of which normal distribution is the most important. Okay? Those were discrete distributions, geometric, Poisson, binomial, all those. Those were discrete distributions, chapter 5. Chapter 6 is the normal distribution, which is our first of several, by the way, first of several continuous distributions. Okay? Don't you love statistics? Oh. So computing normal probabilities. The big difference is probabilities. Well, okay. We even mentioned this last time. Probabilities in continuous distributions are going to correspond to area under a curve. And for the reason I mentioned before, that when you fill up your gas tank, it's 0 to 20 gallons. The probability that you'll put in exactly 8 gallons, 8.00000000, that probability is 1 out of infinitely many outcomes. So the probability of any one outcome in a continuous distribution, as crazy as it sounds, the probability of any one single outcome in a continuous distribution is 0. Because it's 1 out of infinitely many. Okay. Now, we're going to see that here in a second. We're only going to do 2 ways two different techniques of computing normal probabilities. And for that matter, all of our continuous probabilities, we're only going to do two ways. Number one, probability table. Something like that. We happen to have a probability table for the standard normal. For mean 0, standard deviation 1, we have a probability table, right? Right? 2, technology. And I urge you to use technology. I urge you to use the calculator anytime your big mean professor lets you use it. Okay? That being said, I'm going to make you a few times do it by hand. Sometimes I'll let you do it by hand and check it on your calculator, but you have to show all the work as if you did it by hand. So you'll have your calculator to see if you actually got it right, but there's no faking the work. Right? Trust me, I've tried. All right. So those are the two. We're not using. You remember the third way we did for discrete probability distributions? There was a third way of getting probabilities, and that was the P of the PDF. Why aren't we using the PDF here? Because the PDF here is not the probability distribution function. That PDF on the board there for geometric, that's a discrete probability distribution function, right? PDF here is a density function. PDF is probability density function. It doesn't stand for the same thing. And all you get when you plug a value into the PDF, the probability density function, is the height of the normal curve. You get the height of that curve. You know what that tells you? Absolutely nothing. Nothing. Nada. Niente. Zero. Zip. Zilch. So we're not going to use the normal PDF. All right? By the way, it does have uses, but not in here. That's euphemistically beyond the scope of the course. By the way, we do have an intermediate stats class here. Right? So computing probabilities. So for example, in our, right here, shaded area represents the percentage of the area under the normal curve. What is the area under any probability curve? 1. 100%. 1. 0.5 is 50%, right? 0.3 is 30%, etc., right? So the total area under the bell curve is 1. So this shaded area is the probability of seeing a random value with this distribution fall between those two values. The shaded area down here is the probability of a randomly selected member of this distribution falling above whatever value that is. 61. I mean, you don't even know the mean and standard deviation there. But you can see that it's above a certain value. Keep in mind, the tail goes on forever. The tails go on forever, but after about 4 standard deviations, there's like 0 area under those tails to 4 decimal places. Right? So it thins out very, very quickly. Okay? All right? So we're going to think shaded areas for probability here instead of plug in a number and get a probability. Right? All right? Now this is going to be a different kind of twist on the last problem. We're back at Podunk College. Right? Podunk's got a college. Ben doesn't think Podunk has a college. Podunk's got a college. You're going to hurt the feelings of Podunkans. They got feelings too. Graduation time for full-time students at Podunk College is normally distributed with a mean of 4.6 and standard deviation of 0.6, just like the last problem. But we're going to ask different questions. We're going to ask different questions. Last time we just computed z-scores. Here we're going to do something with those z-scores. Okay, that's the difference between this example and the last example. So find the probability that a full-time student will graduate in less than 4.4 years. Right? Now, if 4.4 years happen to be an even number of standard deviations from the mean, you can use the empirical rule. That's only if your data point happens to be an even number of standard deviations above or below the mean, which in real life, doesn't happen. So the probability that a full-time student, a randomly full-time student, will graduate in less than 4.4 years. Now, what is that? So here is our student right here, 4.4, right? This is the distribution of graduation times for all Podunk College students, right? We know the mean is 4.6, so 4.4 is a little below the mean. So the probability that it will be 4.4 or less is this dark area here. That's what we're after, is that dark area. Now, it turns out, and I haven't showed you how to do this yet, if I had a table for mu equals 4.6 and sigma equals 0.6, I could look that right up in the table. But I ain't got one. I don't have that table. But I have a standard normal table. So what we're going to do is we're going to convert 4.4 to a z-score for which I have a table. See how that works? 4.4 is in its distribution, whatever its z-score is in the standard normal distribution. I have a table for that. Okay, so let's see how that works. Right? I'm going to be repeating that. I just wanted to give you a higher level overview before I got into it. And by the way, stop me if something, is.
Yeah, none of this makes sense.
Oh.
I think you'll need to roll back.
Okay. No, you know why nothing makes sense to him is for the last 3 or 4 months he's been hearing me talk about the Bishop's Bible and about the Vulgate and about the Texas Receptus. That's his problem.
Right?
Do you have a class with him?
No.
No.
I have a small group.
Oh, okay. I was like,
He's in.
what class is that?
He and Kelly come to our East Hill small group at our house,
Okay.
which, by the way, all of you are invited to. If you'd like to come. Sunday night at 6. We've been.
That's where my brain went.
Oh, yeah. So, but anyway, so he's been hearing me talk about something entirely different. So conceptually, what we're going to do, 4.4 lies in its distribution. We need to convert 4.4 to a z-score. How do you convert something to a z-score? Subtract the mean, divide by standard deviation. That's how you convert anything to a z-score. So we take, now watch this, Gasapa. Z, x minus mu over sigma. We take 4.4, subtract its mean, divide by its standard deviation. And you remember we call that normalize? When we make a z-score out of 4.3 or whatever it is, 4.4, when we make a z-score out of 4.4, we call that normalizing 4.4, making it a point under the standard normal curve we call normalize, right? So the probability, now watch the algebra here. This is about as advanced as the algebra gets in this class, right? Just about. It gets a little more. But the probability of x less than 4.4, that's what we're looking for. So we translate in our head what the question is asking, 4.4 years or less than 4.4 years. That's that. Now watch what we do. On both sides of that inequality, we take x, subtract mu, divide by sigma. That gives us a z on the left side of the inequality. On the right side, take 4.4, subtract mu, divide by sigma. But we put in the numbers. So that turns the x into a z, and it turns 4.4 into minus 0.33. That is on our table. Okay? That is on our table. Which take a look at this for a second. We'll get to the table. The table is its own ball of fun. Hang with me. So 4.4 is in the underlying distribution of podunk graduation times. It is in that what 0.33 is in this. This is the standard normal over here, right? Mean of 0, standard deviation of 1. Over here, mean of 4.6, standard deviation 0.6. Needless to say, if you don't work with this translation, if you don't go home and do some problems on this, if you don't go home and look at chapter 4 and look at stuff at the end of 4.1, 4.2, look at those problems, I promised Emily I would get a revised homework sheet. I still need that. But you can still go in your book and look. If without doing a few of these, you're going to be a deep kimchi in a hurry. All right? Ask me how I know. Right? Okay? So we normalized, we made a z-score out of it. So back to the question, how do we find out what that area is? We made it a z-score so we could find out that area. How do we find out the area? Now, if you have your book with you, or if you have the formula card with you, get it out. If you have your book with you, or you have this formula card, it is on Canvas. Now, another thing is, oh no. No. Okay. I was getting an attitude. I was getting a major attitude. Okay. In the back spread of your book. So if you don't have the card, just go in the back spread of your book. You have the charts we're going to use. They used to have them front and back. But in the front, what do they put? Blank space and symbol table. Right? Students will use that a lot, right? Okay, back here, back cover of your book, and in page, or the formula card, which I suggest you print out. Okay, the most important thing I'm going to say about this card. Actually, there's two. Maybe three. You ready? It's got a bunch of numbers in it. What are these numbers? Areas under the standard normal curve. Rewind. T-Boo Prof. The most important thing I'm going to say about the card, maybe three things, is that what are the numbers in the standard normal table? These numbers are areas. What kind of areas? Under the curve. Yeah, they are under a curve. That's right. That's right, Miss Emily. She got me on that one. Didn't expect that.
I don't know what you're asking.
Yeah, but watch. Along the sides, the student will observe. Along the left side of each of these tables, you have numbers like 1.0, 1.6, 2.3, right? You have it to one decimal place along the side, from 0, 0, all the way to 3.5. Positive, and 0, 0, 3.5 negative. Okay? So you have it to one decimal place down the side. The second decimal place comes from across the top. For example, in our present case, since it's negative 0.33, we go to the little table that says negative z-scores. Not the positive z-scores, negative z-scores, right? And Jerome left this out of the Latin Vulgate. All right, the negative z-scores. The first decimal place, where do you find it? In your pocket. No, down the left. So we're going to look at minus 0.3 down the left column. So you go do. That's near the bottom. Okay? So minus 0.30 would be that first 0.3821. That would be minus 0.30. We want minus 0.33. So the second decimal place you find across the top. So you got your first one, minus 0.3. You stay in that, and you notice how they have the shaded in and white stripes, it's shaded in white, so that helps you trace it across. And by the way, back when I took this year course, they didn't put stripes on the tables, right? So that's a cool innovation. So you go over here to the 0.03 column. See the 0.03 column? 0.3707. What does that mean? How do I interpret that number? Does everyone know how to find that number? First decimal place down the sides, and that's true for positive or negative. Second decimal place across the top, that's true for positive or negative. So we got our number, 0.3707. How do we interpret that number? It's an area under the curve. Here's the clincher. This puts a bow tie on it. This is the third thing. It is the area under the standard normal curve to the left. And it even says that up there. Standard normal cumulative area from the left. Means that if you start in the left tail, they even got a little drawing up here. If you start in the left tail at negative infinity, and the area under the standard normal curve from negative infinity up to the point that you looked up in the table. So that, back up one here, right here. This is what we looked up. From negative infinity all the way up to the point we looked up in the table is 0.3707. Now, this is with a calculator, but you got the same on the table. So that 0.3707 is the area under the curve to the left. The 0.3707 is the area under the standard normal curve to the left up to the point you looked up. See that? Negative infinity all the way up to there. All right? What does that mean? These are all the points that are less than 0.3 minus 0.33, right? Well, that's going to be the same as the number of points less than 4.4. Now, I know one thing you're thinking, maybe thinking, is why, if this is 0.3707, how come over here it says 0.3694? Did we make a mistake? Never. My pencils don't have erasers. That's baloney. They may not have erasers, but they certainly need erasers. Okay. All right. The reason why this isn't 0.3707 is back here. If you take 4.4 divided by 4.6 or minus 4.6, that is 0.2. 0.2 divided by 0.6 is 0.333333333333 all the way on, right? We had to truncate that at 0.33 because that's all our table got. That's all any of them have. So there's rounding in this answer when you look up on the table. There's a little bit of rounding, right? I will never, since it's probably going to be your final answer, whenever I give you an option of working the problem one way or the other with the calculator or with the table by hand, either answer is good. But you can't round the whole way. That's a big one. You can't round a little bit here, plug that back into your calculator, round a little bit more, plug that result back into your calculator. No. So within the rounding tolerance, these black areas are the same. Now, officially, this one is a little more accurate because the calculator uses 15 significant digits. It keeps 15 significant digits inside, which is why I tell students round only your final answer. Let the calculator carry all those digits. That's what electronics are for. That's what computers do, right? Now we haven't even talked about this in these charts and everything. You're not going to be able. You're not going to. Yeah, that's next steps. Okay. But the way we need to interpret this is the probability that my z-score is less than minus 0.33 is the same as my probability that x is below 4.4. They're the same. And that comes out to 0.3707. Okay. So under the standard normal curve, these are areas on the table. Those are areas to the left. Hidari. That's my one Japanese word. Actually, I know two. Migi is right. Hidari is left. Hidari. A la izquierda. A sinistra. That way. Right? Area to the left under the standard normal curve of this particular value that you look up. That is how you interpret a standard normal table. Okay? And since we can convert any normal data point into a point, we can normalize it to a standard normal, we only need one table. We don't need a table for mu is 4.6 and standard deviation 0.6. We don't need a table for that. We have this. We convert it to a z and look it up on the z table. Right? That was easy. Oh, no. Make that. That was easy. Okay. Using the calculator. How do we use the calculator to get the same result? Right? Okay. Now, I don't have the calculator open. How can I not have the calculator open? That means I taught 2 classes today without the calculator. All right. Yeah, well, calculus, yeah, that's pretty useless in there, right? All right. No, we use the calculator once in a while, just not on tests. Okay, how do you do this? Where are all of the distribution functions hiding on here? In the distribution menu, of course. And that is above the bars key. The
So
bar.
second bars.
Second bars. Second bars. Okay? All right? And look at the top 2 distributions. Normal PDF and normal CDF. What are we going to use normal PDF for? Okay, all together now, absolutely nothing. So in this class, never, ever, never, 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 ever, never, never, ever, never, never, never use number 1.
Yeah, what's the difference between PDF and CDF again?
CDF is the cumulative. So that is the probability of having, for example, up here, the CDF would be the probability of me rolling the first 6 on or before the X roll. So CDF is probability. Let me go over here and do this. PDF for this is probability X equal 6. CDF is probability X less than or equal to 6. Okay. All right. Now, this is for these, for discrete probability distributions. I told you for continuous probability distributions, it's a probability density function. And so PDF just gives you the height of that bell curve. And that height is not the probability of that X occurring. It is not. It's got a use, but it is euphemistically beyond the scope, right? That's one rabbit I won't chase, right? Very interesting, by the way. Very interesting, but we're not doing it. So we are using only the CDF. for any continuous function. So if you go further down here, you have the t. T turns out to be a continuous probability distribution. Chi-squared is a, so some of you are in genetics. Chi-squared, you know, right? We're not going to use the PDF of any of the continuous ones because all it does is gives you the height of the curve. And that is not the probability of that X occurring. Whereas over here, that is the probability of that X occurring. That's a probability distribution function and not a probability density function. It's unfortunate they have the same PDF, the same initials, right? All right, so once again here, if you have a older calculator, you go down to that and you hit plus. And so if you've got catalog help running, you should see this. Okay? You should see that. And by the way, that should work even on the newer calculators. Does it work on yours? It should. However, you're going to have another option. If you would have hit enter, it would have brought you up a menu too. So, but anyway, just follow me here. We'll do the other way. We'll do the other way. Okay. But if you, for those of you with the TI-83 Plus, you always have to hit the plus button. So this is a little cheat sheet application I put on all your calculators. I tried to, that I want you to have on tests, right? You can use it on tests. Anytime you're allowed to use your calculator, you're allowed to use that little cheat sheet function, okay? Because I don't want you to say, what's the first argument in this? Because this has got, look at this. Lower bound, mu, sigma, right? You might forget the order or whatever. After a while, it'll be natural, trust me. But you might forget. I don't want you to get it wrong because you forgot the order. I forgot the formula, right? No. Okay. So now, observe. What do I want? We have a couple ways of doing this. I could do let's do the standard normal distribution. So I wanted, for the standard normal distribution, I wanted the area from negative infinity all the way up to minus 0.33. Okay? So the way you say negative infinity in calculator speak is, there's different ways. The way I like is minus 1 second, comma, 99. You know what that is? That's a negative decimal point, 98 zeros, and a 1. That is a very negative number. Okay? So that's the lower bound. That's basically negative infinity. Comma. Up to minus 0.33. Now, you see these square brackets? You know what that means? That means those are optional. Meaning, not optional, meaning you can go without them, but you got to know what's happening if you go without them. If you go without them, it's going to assume you mean the standard normal. So if I don't specify mu and sigma, it's going to put 0 in for mu and 1 in for sigma. So it's going to do standard normal. And you don't even have to put the right parenthesis, because the calculator will do that for you. Hit enter. Enter. Does that number look familiar? 0.3707. It's the same as we got on the chart, the table.
How did you put the E on there again?
It is second, comma. Second function and then the comma.
Okay.
If you want to, you can just put like minus 1, like, you know, minus 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, just a really big negative number. This is fewer keystrokes, and I'm lazy. I might break a fingernail. Okay. Now, you remember that this had some rounding in it. Remember? And we actually know mu and know sigma. Right? So rather than having that rounding, let's do this again specifying our mu and sigma. Here's the cool part. Ready? Watch this. Second distribution. Number 2. I'm going down here. I'm going to hit enter. I think you just hit 2 and it'll do this. Good. That's what I want, right? Now, it put minus 1 E90. You know what? I said that was a decimal point with 99 zeros. That's the other way around. It's a minus 1 with 99 zeros, then a decimal point. I said that wrong a couple minutes ago. So now I want from minus infinity up to. Now, if I can specify my mu and sigma, I don't need the standard normal. Why did we do mu? Why did we normalize it to begin with? Because we don't have a chart for 4.6 and standard deviation of 0.6. We don't have that chart. The good part is the calculator does have the chart. All right. No, you can't on yours. So yeah, I should have said that. Only the newer operating systems can get that. So for you guys, anytime I hit enter, you guys just hit enter. But for you two, you always have to hit plus. But you can do exactly the same thing. There's no answer that my calculator can get that yours can't. All right. So this screen's a little bit cleaned up. It's a little bit prettier in a way. But so you will do minus 1 E99 after you hit the plus key, comma. And instead of comma, I go down to upper. Now, here's the thing. Why does mu have to be 0 and sigma 1 when I can specify? Why can't I go down here and say, I don't want mu being 0. Oh, it won't let me go down there without this one. So how about if I go to 4.4? That's my original. That's my x. That's not a z, remember? This is before I normalized it. That's an x. And then I don't want that in the standard normal, though, right? The standard normal is only after I normalize it, but it had some rounding error. So let's do it more accurately and say, no, I want this in a distribution whose mean is 4.6 and whose standard deviation is 0.6. So you can put in the mean and standard deviation. It's like you had infinitely many normal tables, right? It resolves the problem that made us use this table. Go down to paste. Now that part should look the same on both calculators, right? Hit enter. And that gives you a slightly different one, 0.3694. You remember if we went back here, right here, this was 0.3694. See right here? Remember that was a little bit different? This one is more accurate. Why? It doesn't have that rounding. Here we had minus 0.333333. We had to cut off after 0.33. Here, it's carrying 15 or whatever decimal places, right? Much, much better, right? Much better. Now, I told you before that the I'm going to give you the option, and I'm going to make you do it by hand once or twice, just so you understand it. But you use the calculator every time you're allowed to. I am saying, though, having done it by hand helps you understand rather than just memorize keystrokes. It helps you understand rather than minimize keystrokes. All right. So here, this explains why it was a little bit different. This explains the rounding problem, right? And we already did this. We already did that one. Did that one. Did that one. Did that one. We're ready for part B. We'll do that one next time. We'll do this one on Monday. We'll start here on part B. Oh, wait a minute. I'm a minute and a half early.
That class is tonight.
It's what?
150.
Is it? Hold on here. Let's look here. I don't believe you guys.
I have 150.
Oh, I have 150 as well. You see my pretty granddaughter? Just kidding. Have a good
Yep.
weekend, guys.
So the quiz on Monday is over
Just
the
the Poisson
Poisson.
distribution. Just the
Okay.
Poisson. And then the next Monday, we'll have it over some normal stuff, okay?
Okay. And so this upcoming week, we're gonna be taking our test.
No, you know what? No, it'll be after. I said something like that, but I misspoke. It's going to be after we're done with chapter 6.
Okay, that's fine.
Probably the week after we get back from spring break.
Okay. And I was gonna ask, so I know that we're taking quizzes for extra not extra grades, but like I guess like
To help you keep up.
right. Or could we do something like if we're taking homework, like if we're doing, or if we do like so many questions out of the book, just to help us cushion with our grade, just because I
Yeah.
feel like I
All
do a lot of questions.
I
and-
might consider something like that. Let me think about that. I don't have any homework built into the class right now because the homework you have all the answers for. But I might consider making a few points homework. It'll be less than quizzes, much less than quizzes though.
No, that's fine, but just like extra credits, or sometimes I like look up like for the but the binomial and the